The next category of secure design principles that we will consider is trust with reluctance. A system is constructed from many parts, and the security of the whole system thus depends on the security of each part. The parts are trusted to varying degrees, and as such, we can improve the security of the overall system by reducing the amount of trust placed in its various parts. And there are several ways to do this. First, we could use a better design. Second, we could implement functions more safely, for example, by using a type-safe language. Third, we could avoid assumptions on which we base our trust. For example, we could avoid the assumption that the third-party libraries we use are actually correct. And instead, we could perform some of our own testing and validation, code review, to ensure correctness and thus establish trust in those libraries. As another example, we could avoid designing or implementing security-critical features that require expertise that we don't necessarily have. A key mistake made by many system builders is to attempt to design or implement cryptography from scratch, something that it turns out is very hard to get right. The principle of trusting with reluctance, when followed, can help prevent security problems and can mitigate problems that might otherwise arise.
One secure design principle that follows the idea of trusting with reluctance is to maintain a small, trusted computing base. The trusted computing base comprises the system components that must work in order for the system to behave securely. As an example, modern operating systems are often part of the trusted computing base because they enforce security policies like access control policies on files. When you have a multi-user system and your files indicate which users are allowed to read and write the file, it is the responsibility of the operating system to enforce those policies. Now, we would like to keep the trusted computing base small and simple to reduce its overall susceptibility to compromise. The idea is that a small, simple trusted computing base is easy for a human analyst to reason about and argue that it is correct. It should also be easier for an automated tool to establish that the trusted computing base is correct. Unfortunately, today, operating system kernels, returning to our example, are not small and simple. Instead, they are often millions of lines of code. Usually the reason is that by keeping all of these different disparate components together in the kernel, we can have higher performance. But we increase the attack surface of the kernel and therefore increase the risk of compromise. For example, a buggy device driver could be exploited and thereby give the attacker access to the entire kernel. The kernel's trusted computing base, that is, the parts enforcing security policies, could therefore be subverted by the attack via the device driver. An alternative design is to minimize the size of the kernel so as to reduce the trusted computing base. For example, device drivers could be moved outside of the kernel, and therefore a compromise of one of these drivers does not compromise the portion of functionality that enforces security policies. This sort of design is advocated by microkernel architectures, which were popular in the 90s and are regaining popularity today. As another example of a failure to follow the principle of a small trusted computing base, consider security software. This software is obviously part of the trusted computing base because it is used by the system to enforce security. In other words, to make sure the system is free of viruses or worms and the like. Unfortunately, over time, this software has grown in size and complexity and has now become vulnerable itself and is frequently attacked. This chart, put together by DARPA, shows that 6 of the vulnerabilities reported in August and July of 2010 were in fact in security software. Now let's consider another principle that follows the idea of trusting with reluctance, and that is the principle of least privilege. This principle states that we should not give a part of the system more privileges than it absolutely needs in order to do its job. This is similar to the idea of need to know, not telling someone a secret unless they really need to know it. And the motivation is the same. We want to mitigate any effects of compromise. If a component is compromised by an adversary, we want its capabilities to be limited so that the adversary's power is also limited. As an example, consider the idea of attenuating delegations to other components in the design of a system. For example, a mail program might delegate to an editor for authoring emails. This editor could be VI or Emacs, which are both very powerful editors, and both very desired by users. Unfortunately, these two editors and others permit too much power. For example, they permit escaping to a command shell to run arbitrary programs. This is too much privilege for an email program, because if we gave an untrusted user access to the email program, they could author an email and then use the delegated email editor to execute arbitrary shell commands. A better design is to use a restricted editor that only allows the user to perform the functions that are absolutely necessary to author emails. An important lesson here is that trust is transitive. If you trust something, you trust what it trusts. And of course, that trust could be misplaced. In our previous email client example, the mailer delegates to an arbitrary editor, and that editor permits running arbitrary code by delegating to a shell. Hence, the mailer permits running arbitrary code. This is probably not what we had in mind. The rule that implements the principle of least privilege is input validation. The idea here is to only trust inputs that we have properly validated. That is, we don't want to trust any input. Instead, we want to establish trust in that input by making sure that it follows an assumed format. In short, we're trusting a subsystem only under certain circumstances, and we want to validate that those circumstances hold. So we have seen several examples of this so far. We can trust a given function only if the range of its parameters is limited, for example, to be within the length of a buffer. Or we could trust input taken from a client form field on a web page only if it contains no script tags and therefore is not subject to cross-site scripting. We could trust a YAML encoded string, but only if it contains no code. So by validating the input, we are limiting the influence of that input and thereby reducing the privilege that we are replacing in the components that process it. Another secure design principle that aims to trust with reluctance is promote privacy. Broadly speaking, a manifestation of this principle is to restrict the flow of sensitive information throughout the system as much as possible. Basically, the idea is that only those components that have access to sensitive information can possibly disclose it, and therefore by limiting access, we reduced the trust in the overall system because we don't have to trust as many components. As a result, we are mitigating the potential downside of an attack because fewer components that could be compromised will be able to disclose that sensitive information. As one example of this principle in action, consider a student admission system that receives sensitive letters of recommendation for those students as PDF files from recommenders. A typical design would allow reviewers of student applications to download recommendation files for viewing onto their local computers. The problem with this design is that compromise of the local computer will then leak private information contained in the PDF files. A better design is to then permit viewing a PDF only in the browser as opposed to downloading it to the local computer. As a result, if that local computer is compromised, no sensitive data is available for access by the attacker. The last design principle that we'll consider that has the flavor of trust with reluctance is compartmentalization. This design principle suggests that we should isolate system components in a compartment or sandbox and thereby reduce the privilege of those components by making certain interactions or operations impossible. In this way, we can prevent bad things, that is, those only enabled by the operations that we're not allowing, and we can mitigate the results of an attack by preventing the compromised code from doing anything beyond what the sandbox would allow. As an example, we might disconnect a student records database from the internet and grant access only to local operators. This compartmentalizes the student records database, therefore preventing attacks from the outside. Just as importantly, if a local operator attempted to compromise the database and exfiltrate the data, they would not be able to do that via the internet. Another example of a mechanism for compartmentalization is the seccomp system call in Linux. This system call enables us to build compartments for untrusted code. Seccomp was introduced in Linux in 2005. The way that it works is that the affected process can subsequently only perform a limited set of system calls: read, write, exit, and sig return. Notice that there is no support for the open system call. Instead, the compartmentalized process can only use already open file descriptors. Seccomp therefore isolates a process by limiting its possible interactions to only these system calls. Follow-on work produced seccomp BPF, which is more general. In particular, it allows us to limit a process to a policy-specific set of system calls rather than just the 4 I just listed. This policy is enforced by the kernel. It's specified by something like Berkeley Packet Filters, or BPF. Seccomp BPF is used by Chrome, OpenSSH, VSFTPD, which is the very secure FTP daemon, and others. So let's look at how we might isolate Flash Player that aims to execute a file that we browse to on the internet. First, suppose we browse to a website that has a shockwave file, which is a program that's going to be run by Flash Player. As usual, we'll save this file to the local machine. Next, we'll call fork to create a new process, and that process will open the file. Now this process is still running as Chrome, and so we must exec the process to now run as Flash Player instead. Now before the process can get much further, we call seccomp BPF to compartmentalize it, limiting the system calls that it can perform. In particular, we do not allow it to open network connections, and we don't allow it to write files to disk. That way we can ensure that Flash, if compromised, will be limited in the damage that it can do.